the second in our series of MGIS talks. We're here today to hear from Nate Geyer, Max McDonald, and Ben Martini. We're all really happy that they're able to wrap up their MGIS. They'll all three be graduating here in August, and we're looking forward to hearing about their capstone work today. Call attention to our question period. As you develop questions, you can put them into the chat area, and then at the end of our talks, our presenters will work through those questions. Our first speaker today is Nate Geyer, and he will be sharing his work to develop LionView 2 and the usability assessment for Pennsylvania. So go ahead, Nate.
Hello, ladies and gentlemen. My name's Nathaniel Geyer, and I'm doing a presentation, as Doug said, on LionView 2.0. LionView is a prototype that was developed by Dr. Gene Language that has to do with cancer mapping in the health field, and I developed a prototype, which I'm going to show later. The summary of this talk is going to be objectives, methodology, results, and discussion. And here's an example of the prototype that I developed. One of the concerns about LionView 1.0 was that only one map could be shown at a time, and like most web maps, and it was done using Esri, so it couldn't be localized, and the JavaScript was obsolete, and it's constantly changing every 3 months, so it made it difficult to. So in light of all these things, I developed this prototype. It was developed using Leaflets 1.6.0 with 3 plugins in jQuery. The data that I used was Census, Medicare, County Health Rankings, Pennsylvania Department of Health, HRSA, and PSCI. The color schema was based on Color Viewer 2.0, and it also illustrates side-by-side user interface with 2 iframes. The objective of this survey was to conduct a usability assessment of Line 2.0 using domain expertise to explore cancer data. I first developed a survey assessment questions, distributed the survey via RedCap survey system. I analyzed qualitative survey data using open-ended via content analysis, perceptions, and closed-ended via item analysis for evaluating patterns in cancer data, task completion, accuracy, and time. The target audience was Penn State Cancer Institute faculty and staff, PSU University Park faculty, Pennsylvania Department of Health Division of Cancer Prevention and Control, Penn State College of Medicine faculty, and others like St. Joseph's and PSU Harrisburg, etc. The LionView assessment survey contains 5 demographic questions, 4 employment characteristics, web map proficiency scale, which I asked the person about how comfortable they were with web maps, and I wanted a self-assessment and a quantitative assessment on how to improve the thing. So I needed to ask a question. I also asked 3 CDC web map questions in which I asked the audience how to use a pre-existing web map. I had 10 to 20 task-related questions, 5 questions per task, 5 Likert scale, 10 open-ended general feedback questions, and the RedCap survey system. It builds online surveys and databases quickly and securely. export data to common data analysis packages, Penn State College of Medicine based, open to professionals from other Penn State campuses, including World Campus. Participants were by invitation only, not general public, program managers, epidemiologists, clinicians, and faculty. The response rate, there was 123 invitations, 23 individuals started survey, 10 completed entire survey. Completion time, I was expecting it to be 30 to 40 minutes. The median time was 50.5 minutes, with the confidence interval being 37 to 71.5. The demographic questions, the median age was 56 years. The race was 71% white, 19% black, and 19% Asian and 10% black. Ethnicity was 15% Hispanic. The gender was 55% females. The education, 65% doctorate, 15% professional degree, 15% master's, and 5% bachelor's. The employment, the location was mostly at Hershey, 65, with 20% State College and 15% in Harrisburg. The work type was 70% faculty, 15% manager, 10% clinician, and 5% staff. The organization was 45% Penn State College of Medicine. That includes the department where I'm located, Public Health Sciences, 20% Penn State Health, 20% Penn State University Park, 10% Department of Health, and 5% Penn State Harrisburg. There was nobody who was found at St. Joseph's. Please rate your proficiency using web mapping tools. As I said before, this was developed for self-competency, 45% fundamental awareness, 25% limited experience, 20% intermediate, 10% advanced, and 0% experts. The CDC web map from the rate of new cancers in Pennsylvania. In this web map, what was the age adjusted rates of new cancers in 2012 to 2016? In order to do this, you had to move this radio button to here, and it gives you the correct answer. However, when I asked that question, only 13% were able to answer it correctly. The limitations were poor data availability, hard to use, and overwhelming. Strengths were ability to manipulate data, broad scale, and easy at a glance. The expectations, it meets expectations, and the capability data can be used up to state level with no sub-county data. In my prototype, where I asked what was the population density of Luzerne County, which is right here, and the color ramp, which is right here, 92% answered that correctly. However, because of this label was difficult to tell, only 58% answered that correctly. And many people were unable to find documentation. Color scheme was different for Pennsylvania and catchment area, and there was inconsistent county labeling. These were some concerns. In another test where I asked what was the density of endoscopy providers in Lancashire County, which is right here, 90% answered that correctly. However, when the provider was not found within, which is this one in York County, only 30% were able to answer that correctly, mostly because the audience was mostly used to using chloroplast maps, and this was point data. And I got some feedback to include tabular data instead of going to each point, better description and annotations. And now for the next thing, task where I rated my experience using LinePoint 2.0 prototype, with 1 being strongly disagree and 4 being strongly agree. It is easy to move from different points of the user interface. The median was agree. I can easily access information displayed in the map. The median was also agree. It is easy to remember how to perform tests. The median was strongly agree. The system was reliable. 4 was strongly agree. And the maps were easy to understand. 3 agree. And some feedback, if the response was not strongly agree, please provide feedback. It is easy to move from different points of the user interface. Checkboxes need to be persistent on the page. Easier to locate documentation. Remove zoom on click functionality. Difficult to deselect layers using checkboxes. I can easily access information displayed on the map. Better referencing of sources to minimize going back to cited sources. Quantitative quantiles were not easily standardized across measures, so it is somewhat challenging to interpret comparisons. If this was not strongly agreed, please provide feedback. It is easy to remember how to perform tasks. Better ability to dig deeper to specific sources instead of the general web pages. And I also got feedback to include a 15 to 10-minute video to provide training for users. The system is reliable. The only feedback I got from that one was increased lag time between selections and screen displays, and which the maps were easy to understand. It was unclear how to interpret the results when multiple checkboxes are selected spontaneously. Corpot map for point data showing location. Clinics having a list on the screen would help with figuring out locations on a map. For what you see as the primary purpose of the LineView prototype, it is helpful for researchers interested in writing grants, quick views of local data, used by Penn State Cancer Institute members to access different variables in the catchment area to aid in research, geographic analysis, summary of existing data with easy visualization, teaching tool for students. Please elaborate on your thoughts of what kind of functionality do you consider to be essential for LineView 2.0, easier to export to an image file, ability to produce tables, persistent layer selections, remove zoom on click functionality. Please elaborate on whether the prototype provides you all the tools you need to do your job well. I like what I see at this time illustrated for teaching, usage for classroom discussions as needed, not related to my career. Some selected side-by-side responses of timeline to completion. One suggestion was better referencing of sources to minimize going back to cited sources. Direct hyperlinks were avoided in case the link gets changed, rendering it to be invalid. Better ability to dig deeper to the specific sources instead of the general web pages. Hyperlinks may change, making the links invalid. We'll work on improving the links and help documentation. Lack of standardization of quantiles. Aim to standardize quantiles. Include a 10 to 15-minute video to provide some training to users. What are some suggestions on training topics? Will be developed by December 2020. Use up-to-date data set. Will include more up-to-date data. The timeline for the release from July to August, I did some programming fixes. I found some complete data sets, explore server options, which I'm still planning on doing, in manuscript submission for this usability assessment. September, programming fixes and implementing complete data sets. October, programming fixes and move to a new server. November, training vehicles, videos, and help documentation. And December, release of LineView 2.0. The next slide is an example of something I developed yesterday on the LineView 2.0 update. On this one, I kept the two iframes, but I added a pop-up for documentation. So when they log to the website, this information screen with some documentation is included. I also split the cancer data into mortality incidence and early stage percent, and the cancer to late stage percent. And I also went through and made sure that all data that I had was included. It's still a working progress. Another feedback I got was that the control layer list was not persistent. So I removed the collapsed option and made this layer list persistent. Another feedback that I got for the downloading images, I had the printer option below the zoom thing. It's right here, but it only printed things out for people who wanted to save to an image. I removed the printer. I found that they updated documentation for this plugin leaflet browser print that allows scrolling and downloading to a ping image. So that was something I added. That includes this web map, the scale bar, and the annotations. But as I found with Legends, I wasn't able to include that onto the image, but I'm still working on that. Here are some references of sources I use and some acknowledgments. Is there any questions?
Okay, thanks. Thanks, Nate. Audience, if you want to share your questions in the chat area, we'll monitor those. And Nate, as you see them come up, you may go ahead and answer them.
I don't see any questions. Hi, Nate. What do you think you'll do differently now if you were able to do the study again with a different user population? Yes, there are some things I would have done. In the original group, I did not include students. I found that some of the respondings I might include more students involving this into pre-existing coursework to see how students would interact. I proposed that in my documentation, but yes. And another question I had about PA specific application, it could be done. The challenge is that the shape files and the GeoDA files that are in there, I excluded all the other states, but it can easily be replicated for other states. Yes, that's not a problem. Is there any other questions?
Okay, thanks, Nate. We'll move to our next speaker. Max, if you want to share your screen, we can get started when you're ready. Nate, thanks for your presentation. And
hold on a second, I got another.
There is. Yep.
Yes, the length of
Go
this
ahead.
survey instrument was 50 questions. In the future iterations, I might want to decrease the number of questions, but still keep the content. Are there any other questions before we move on? I think we can move on.
Okay, Max, go ahead and share your screen when you're ready, and we'll get started.
Max, we don't hear you yet, so you might be muted.
Okay, sorry about that. You guys can hear me okay now, right?
Yes.
Okay.
I don't see your screen.
Yep, I'm getting that back up right now. All right. All right. Thanks, Nate. That was a great presentation. Hello, everyone else. Thank you to anyone not presenting who has taken time out of their day to be here. My name is Max McDonald, and this is my capstone project presentation for the MGIS program. The topic I'm discussing today for you all is the use of GIS in transportation planning and decision-making. Here, GIS software is used in a proof of concept study, proposing an alternative corridor for the Virgin Trains high-speed railway that's going to go between Victorville, California and Las Vegas, Nevada, as well as its anticipated impact on Los Angeles County's transportation access to Las Vegas. You may be thinking, well, how did Max choose such a topic? Well, as fellow geographers and academics, I hope we can all agree that in research, the question is not always who, what, why, or how, but also where. As founder Jack Dangerman said regarding Esri's new brand emphasis, where is what we do every day. Jack certainly was addressing Esri and Esri's end users' values, but I'm certain he'd agree that this applies to all geographers, even the non-Esri users. So no matter your software preference, what drives us most as geographers is where, then some combination of who, what, why, and how. Thus, one day in 2019, I was searching my mobile device's map, pondering where. Where can the United States use a new railway the most? My questions led me to Las Vegas and my curiosity to the discovery of the Virgin Trains high-speed railway project for 2023. I quickly discovered the Virgin Trains project aims to reduce a 4-hour car ride to 90 minutes by traveling roughly 170 miles at 130 miles per hour. The project is primarily backed by Fortress Investment Group, as well as the California Infrastructure and Economic Development Bank. It's aiming to be fully operational by 2023, and the venture is projected to cost $4.8 billion, and Interstate 15 is Virgin Trains' chosen corridor for the construction. It will first connect Victorville to Las Vegas, with plans to eventually extend to Palmdale, California, and downtown Los Angeles. I decided upon 2 objectives with which to conduct research on and perform spatial analysis in Esri's GIS software, ArcGIS for desktop. First, I propose an alternative corridor for the high-speed railway using least cost path analysis. I've taken a multi-criteria evaluation approach to determine which corridor is least costly in terms of length, most efficient regarding the landscape, and safest in terms of who or what can be involved in an accident. Second, I conducted a system-facilitated accessibility analysis of the current and future states of Los Angeles County. In this study, system-facilitated accessibility is described as the level of effort required for an entity to travel among a transit network. And the current and future statuses refer to the existing road and highway network and the anticipated inclusion of the new railway to that same network. A least cost path, or LCP, is derived from raster data. 4 raster surfaces are required to do this. First, origin and destination cells. Second, a cost surface. This project uses an accumulated cost surface, which is comprised of multiple raster surfaces representing the 3 evaluation criteria I just identified. Finally, LCP construction requires cost distance and cost backlink surfaces. So I'm going to explore these inputs individually. The origin and destination are represented here, along with the Virgin Trains corridor within the study area. No data yet exists for these points, so the two stations were arbitrarily dropped on the map according to their location descriptions. There are varying criteria that the LCP is proposed under. Multi-criteria evaluation is enabling the best solution dependent upon multiple criteria. Through Thomas Soddy's multi-criteria evaluation procedure, the analytical hierarchy process, I proposed percent influence criteria weights for the spatial analyst weighted overlay tool with a pairwise comparison of 5 subcriteria. These 5 subcriteria not only represent the 3 evaluating criteria, but also the data sources from which the individual cost services are accumulated for the accumulated cost service. Before I speak to those data sources, I'm going to talk about the analytical hierarchy process, or AHP for short. AHP is commonly performed to create accumulated cost services. It enables decision makers to arrive at a scale of hierarchy drawn from a set of alternatives. The 5 cost variables here are the basis for such a hierarchy regarding suitable HSR corridors. Through a pairwise comparison matrix, 2 variables are compared at once, rather than all variables being compared at the same time. This results in an aggregate best choice hierarchy of the criteria under evaluation. In other words, each cost component of the LCP are compared one at a time, row by column, and ranked according to the user's perceived importance of a row over each column. A value higher than 1 is considered important, and values lower than 1 considered unimportant. The pairwise comparison matrix is the first step in AHP and is usually the product of multiple stakeholder and experts' knowledge and opinions regarding a problem. In order to get the criteria weights, a normalized pairwise comparison matrix needs to be created. One normalizes the pairwise comparison matrix by dividing each cell by its sum of the column. Afterwards, the criteria weights for the weighted overlay tool can be calculated. This is done by taking the sum of each normalized row and dividing by the amount of criteria. While the criteria weights are established early on, there exists 5 more steps in the AHP procedure, which develop a consistency ratio that evaluates randomness in the rankings presented in the original matrix. Between 0 and 20% is the usual accepted range for a consistency ratio, and the example here is judged by a consistency ratio of 25%. So the judgments here have a slight touch of randomness, but only serve as an example. In this study, I did not consult with multiple experts or stakeholders of the Virgin Chains project, but instead deployed AHP as a proof of concept. I created 5 pairwise comparisons, each favoring a criterion, and then averaged the results together to form a best attempt at a realistic pairwise comparison that would have normally been determined by experts and stakeholders for LCP analysis. After creating an aggregated pairwise comparison matrix from the 5 subcriteria, the data representing them is prepared to be entered with their real weights into the weighted overlay tool. As you can see here from the table, 2 data items are already in raster format, and the rest are in vector format. All data items are projected to reference the Harn State Plane California Zone 5 coordinate system in US feet and clipped to the study area. The vector files are converted to raster format, and all subcriteria data are reclassified to form individual cost services on a 1 to 5 low cost to high cost scale. The land cover land use data is reclassified based on its NLCD classification, the slope by its percent rise, roads by their type, national parks by whether they exist or not, and finally, infrastructure proximity, which is reclassified by a series of buffer ring distances around the cell that represents its location. The resulting accumulated cost service is represented here, and the pre-processing stage for LCP analysis has concluded. The green areas represent low cost cells, yellow medium cost cells, and red the costliest cells. All that remains is to create the cost distance and cost backlink services and run the spatial analyst cost path tool. The spatial analyst cost distance tool takes the origin and destination cells and the accumulated cost service and outputs these 2 raster services. The cost distance service helps ArcGIS calculate the least cumulative distance to the destination, and the cost backlink service determines the next neighboring cell that is in the direction of the least cumulative path to the origin. To help you better understand the cost backlink service, each cell is assigned the direction towards the next cell on the least cumulative path to the origin. So for example, if a cell is a green color, the next best cell is in the northern direction towards the origin. All 4 components are then used in the spatial analyst cost path tool, which the LCP is created from. The LCP is displayed here in contrast to the corridor chosen by Virgin Trains. Visual analysis is not enough to evaluate these corridors for effectiveness. Therefore, I use the spatial analyst extract by mass tool to extract the cells under each of the vector polylines within the accumulated cost surface. I discovered that the LCP is 31% shorter than the Virgin Trains corridor. This table displays the total amount of cost cell categories that the LCP and Virgin Trains HSR corridors accumulate. The LCP traverses significantly more low-cost cells at a 1 to 51 ratio. It's also discernible that the LCP corridor traverses a considerably less amount of medium-cost cells at roughly a 1 to 204 ratio. Otherwise, the path traverses no high-cost cells, while the Virgin Trains corridor traverses a total of 105. Overall, it could be said that the LCP is significantly better in terms of cost, efficiency, and safety. However, it is interesting to note that when the extract by mass tool is run on the same two corridors using the individual cost services of each subcriteria, the only categories that the LCP totally wins out on are the infrastructure, proximity, and national park existence categories. The LCP is marginally better in the land use and road type subcriteria categories, but the slope category indicates that the Virgin Trains corridor is more suitable. This I primarily attribute to the AHP pairwise comparison matrices and the development of similar criteria weights, of which received a consistency ratio of 24%. The eventual Virgin Trains Railway will be the only way to venture to Las Vegas from Los Angeles by train. For the system facilitated accessibility analysis, I've taken my LCP, seen here as the orange polyline, and included it into the existing railway network. I created a network dataset in ArcGIS that includes this railway network with the LCP corridor as the pseudo Virgin Trains HSR, as well as the green and gray Tiger Line road polylines used earlier in the LCP analysis. A properly constructed network dataset can solve the fastest, shortest, or least costly route through multiple groups of transit networks. Here there are two groups, the roads and the railways. In order to measure the change in system facilitated accessibility, the network dataset I created has a restriction option to solve routes only through the road network. This is specific because the study assumes that a person would not purposely drive to take a train, then get off the train and start driving again with their own car or otherwise. Therefore, the current state of system facilitated accessibility will assess the level of effort it takes to reach Las Vegas by car, and the future with the option to travel by car and or train. It's important to measure changes in accessibility when justifying a transportation project such as this one. Public transportation exists to easily move multiple passengers from one location to the next at a reduced level of effort that it would normally take a single entity to do the same for itself. What's the point of spending the time and money if the project isn't going to increase access of a location for people? Measuring the effort it takes to traverse the two states of the network dataset can be broken down into two equations. The first equation, private cost, represents the level of effort by car, and the second, HSR cost by train and or car. The network datasets are comprised of cost impedance fields among its elements that represent costs such as the amount of money spent on gas, the amount of money spent on train fares, the length in feet or miles, as well as the time in hours or minutes spent per polyline feature. The Network Analyst Solve tool will accumulate these impedance fields with every route solved, with which we'll plug into the equations above. To note, value of time in the study for private transportation costs will be fixed at a higher number, 2 rather than 1, due to the assumption that someone with a sense of urgency would not rely on public transportation. My geographical zones for this objective are the census tracts of Los Angeles County, also downloaded from the US Census Bureau. In order to solve a route for 2,346 tracts, I calculated centroids of every census tract feature and snapped those centroids to the road network. The centroid creation process was also done for the center of Clark County, Nevada, which happens to fall inside Las Vegas, and this acts as the destination for this analysis. The Los Angeles tract centroids are then split by their unique field ID that I've given to the polygon feature class and represent our individual census tract origins. Next, each origin is merged with the destination centroid in Clark County via Python scripting and saved as their own feature class called stop 0001, 0002, etc. These 2,346 pairs of stops were then put through a lengthy batch Python script to solve each of the routes twice, once with the driving restrictions for the network dataset and once without the restriction. If you can interpret the Python script, you'll see that the routes are saved like the stops as their own feature class called route 0001, etc. Once the Python script is finished executing, there exist two groups of 2,346 individual routes. The two groups of routes are then merged as two separate feature classes, one representing the car routes and the other the train and or car routes, which I've creatively named merged routes and merged train routes. Here you can see every route, some overlapping with each other from the individual census tract origins to the same destination in the center of Clark County. Using the cost impedance fields the routes have accumulated, these new feature classes are given the fields drive access index and train access index, respectively. Following, they're calculated via the system-facilitated accessibility equations I mentioned earlier. This grants me each census tract's level of system-facilitated accessibility to the center of Clark County, and to say the least, the results are interesting. After joining the route information to the original census tracts by the respective ID field, I can display the results. Here are two thematic maps representing the level of system-facilitated accessibility for the current and future states of Los Angeles County. The patterns of accessibility in LA County are very complex due to the transportation network. Any change to the transportation elements or their impedance fields would affect the patterns of accessibility displayed here. Notice the concentration of light yellow and white areas in the southwest left map, indicating that Las Vegas is harder to access the further in distance you are away. On the other hand, the concentration of dark red and orange tracks in the northeast indicate the places close to Las Vegas have an easier time assessing it. Over in the right map, you can see that the same southwestern concentration with some areas showing improvement in system-facilitated accessibility. Subsequently, not all the northeastern tracks have the same access compared to others now that the Virgin Trains Railway has been considered. No matter the chosen corridor, the Virgin Trains project will surely increase the level of system-facilitated accessibility LA County has to Las Vegas. As shown in this third thematic map, only 5 census tracts experience a -% change in access. The null value appears in the table due to the existence of Santa Catalina Island off the coast of California, where a route over the water could not be solved. The areas that experience a negative change, based on my network analysis model, are attributed to the fact that they do not lie near a major road or highway, as well as lie close enough to a train station on any railway. Therefore, based on the analysis I presented before you all today, 99.7% of Los Angeles County will experience improved access to Las Vegas once the Virgin Trains high-speed railway project is operational. As I presented here, GIS can be a useful tool in transportation projects. The ability to rapidly visualize alternative corridors for travel and quickly evaluate the level of access they can provide can be an invaluable tool in planning and decision-making. I'd like to give a special thanks to the 3 people who worked with me throughout the entire Capstone experience. Your commitments to excellence in geography have inspired me every day. Thank you. Here's some of my references. And does anyone have any questions?
Thanks, Max. Sorry.
Okay.
Do we have questions from the audience? I see Pat Kennelly and Nate Geyer both have questions there. So
Hold on.
go ahead.
I'm having trouble viewing the chat. 1 second.
Okay.
Here we go. Okay, so Nate asked, what datum did you project the rasters for? Did you project the rasters for the analysis? So the datum, there's not any elevation data in the network data set, so the datum wasn't any concern. But as you can see here, the originating coordinate systems and datums for each of the data types in this table. Ultimately, we just used the state plane California Zone 5 in US feet as far as the projected coordinate system. And then Pat asked, are there specific advantages to the current Virgin Trains Plan Cs to the following I-15 corridor? So not a lot of information exists regarding, first off, regarding the locations of the stations as well as the corridor. It is evident that they're going to build it along Interstate 15, as Professor Fritz and I were discussing. We're unsure if that's through the middle of Interstate 15, on the side of it, a few feet off to the side, etc. So we just had to assume that it's going right along it. All the information that I got as far as the location for the stations and the I-15 corridor is just based off of the Clark County Commissioner Board meeting and some news stories that report on the subject. That being said, I could have used the I-15 corridor in the network data set. However, the issue as far as building a network data set with a vector representing the actual road and a vector representing the train line have a problem due to coincident lines. If they're so close to each other when constructing the network data set, it just assumes both the features to be one and merges it together to the point where routes can't be solved over the train line. It'll just choose the road every time. So I think the advantage on their side as far as picking it, we predict to be the fact that the land's already owned by either San Bernardino County or just the local government. Another reason would be that, in fact, that the the road exists there. It's the most direct route. And as you can see from the extracting my mask on the slope cost surface, it is the better route. So I think my prediction would be that the slope percent rise would be the primary concern for building the line. They don't want to cut and fill across another part of the landscape. And then Travis asked, what's the underlying cause for the difference in the train routes? For example, are there other data sources that should be considered in the least cost path? Yeah, of course. So when you're doing an analytical hierarchy process, it's recommended that you use anywhere from 5 to 9 criteria. In this case, we use 5. The analysis is data-driven, meaning that it's constrained by the available public data. So from my knowledge and lack of expertise in regarding high-speed rail construction, I could come up with these 5 only. There's certainly other data that exists, and as I go through the next year, one of my goals is to improve that amount of data to put in the analytical hierarchy process, as well as have stakeholders and experts like do the AHP process themselves. I would say that the criteria weights are the primary motivators for where the LCP lies as compared to Interstate 15. But why, I may have missed this, but why is slope weighted highest? So as you go through the analytical hierarchy process, so as I just explained, I didn't consult experts or stakeholders, but I used 5 different pairwise comparison matrices to aggregate together and average the results. So each of the 5 pairwise comparison matrices represented one of the criterion. So one was as if a stakeholder or expert was favoring the land use data, or the other one would be slope or infrastructure proximity, as if someone was concerned about each one. So in each of those individual pairwise comparison matrices, for example, if someone was representing the slope percent rise, you would see slope rated as most important across all categories. In this case, I think in this slide, it's the land use one, but this is just an example. So the resulting pairwise comparison matrix that develops the criteria weights in this slide, you see that slope actually comes out on top by a margin. So depending on the ratings and the scale ratings, and for example, I use 1 to 3 here, you can use up to 1 to 9, like 9 being most important and 1/9 being the least important or shouldn't be considered. You can get a more disparity in between these weights. Slope is only weighted highest just based on the average of 5 pairwise comparisons. That being said, it would all depend on who's constructing the HSR and who, whether safety is the most important, like if they don't want to come near a hospital or a school, or if in this case slope is more important, considering they didn't want to cut and fill across San Bernardino County for a more direct route. They just used the route that's already there. I hope that answers your question. Does anyone else have any questions?
Okay, thanks, Max. If there are no further questions, we will move to our final speaker of the day, Ben Martini. Ben will be sharing his capstone work at JFK Airport, and I'll let him share his screen, and he can get started whenever he's ready.
Mic's working right? Everybody can hear me? I've just got to get the screen up here real quick. Can see the screen too?
Yep.
Yes.
Yep.
There we go.
Audio and visual good.
Okay. All right, well, good afternoon, everyone. Congratulations to the earlier presenters, both very interesting talks, and thank you all for coming to the capstone presentations today. My name is Ben Martini, and I work as a wildlife specialist for the United States Department of Agriculture in New York City, in addition to being an MGIS student. And today I'll be discussing my capstone project, which is titled Using Object-Based Image Analysis for the Detection of Laughing Gull Nests. So I'll be covering quite a bit in my presentation, and just to give you guys with a brief outline, I'll first be discussing the background of the project and the work that I'm going to be building off of. I'll then discuss the methodology that we implemented to carry out the project, which includes the workflow and how we built a rule set to extract laughing gull nests from aerial imagery. And finally, I'll wrap up the talk with an overview of my results and then discuss what that means for both this project and for the wildlife field. So wildlife hazard management is a major part of airport operations due to the human safety risk that wildlife can pose to aircraft. The most famous example of a wildlife strike that almost everybody's familiar with is the crash of US Airways Flight 1549, which struck a flock of Canada geese on departure from LaGuardia and was forced to ditch in the Hudson River. Now, the FAA has long mandated that all airports have a wildlife management hazard plan because of this risk. And the airport that I work at, the John F. Kennedy International Airport, has a very comprehensive management plan, and part of that plan deals with one species in particular that they have a lot of issues with, which is the laughing gull. Now, the laughing gull is a protected bird in the United States under the Migratory Bird Treaty Act, and it's also a species of interest to New York State. At one point, it was extirpated as a breeding bird from the state due to human pressures and did not reestablish itself until the 1970s when 15 breeding pairs were discovered in Jamaica Bay, which coincidentally is adjacent to JFK Airport. Now, between 1988 and 1990, airport staff noticed that the majority of strikes that were happening at the airport were due to laughing gulls. So they developed an integrated damage management plan that centered on a lethal removal program to reduce the strike risk that these birds were causing. And because this plan had a lethal component, they implemented an aerial surveying program in 1997 to monitor the impact that their management plan was having on that nesting population due to its importance. So between 1997 and 2017, aerial surveying was conducted what I like to call the hard way, using large panchromatic aerial photos, clear sheets, a magnifying glass, and a marker. The maps were printed out and broken down into a grid using the clear overlay sheets, and then you take the magnifying glass and the marker and you go off on your way looking for all the nests in the imagery. And this was supplemented by a triennial ground truthing survey to determine a correction factor that would be applied to the final estimate. Now, there are two big problems with this method. As I can attest from personal experience, it's extremely time consuming to do this, and it's also prone to human error. You might miss nests in the imagery when you're looking for nests during your initial search, and you may miss nests when you have to go back and total each grid cell for the imagery to determine the final estimate. So in 2018, we made what was perhaps one of the biggest changes at this point to the methodology, which was to incorporate ArcGIS Pro into the project. Now, this entirely eliminated the need for the grid system and going back to recount nests, because now all you had to do was look at the attribute table to find out how many nests you had identified. But this project is still subject to problems with efficiency and human errors. So in searching for a solution to these problems, we hit upon object-based image analysis as an appealing alternative. Object-based image analysis is a relatively new remote sensing technology that's gaining traction for monitoring wildlife populations and presented us with a potential solution to our efficiency and human error problems. And it's already been implemented several times to search for wildlife. In 2011, it was used to identify lesser flamingo populations at the Campers Dam in South Africa. And in 2017, it was used to detect white-bellied sea eagle nests in Western Australia. However, it's still not a widely used technique in the wildlife field, which presented us with a gap to contribute to the growing understanding of this methodology. So we developed the following goals to leverage object-based image analysis technology to improve the laughing gull nest survey at Jamaica Bay. First, I wanted to improve the efficiency, cost effectiveness, and reduce human errors of the Jamaica Bay Laughing Gull project, as well as contribute to the growing body of literature documenting the value of these techniques and methodologies for monitoring wildlife populations. And this would primarily be accomplished by designing and developing a comprehensive object-based image analysis methodology that built upon the existing methodology we had to find laughing gull nests in the aerial imagery of Jamaica Bay. So that's about it for the background of the project. Now I'm going to move on to how I accomplished the work. So to first orient everyone with the study area, here's an overview of the tri-state area. JFK Airport is located in Queens, New York, shown as a yellow star in the image. And zooming into that yellow star, this is our study area outlined in pink. Joko Marsh is a 130-hectare salt marsh, and it contains 99% of the breeding laughing gulls in the entire state of New York. And you can already see just for looking at this overview map why it's such a problem, as it's located directly adjacent to the end of the 4 left, 22 right runway. So to implement this project, we used the following 4 data sources. We had access to 2 sets of high-resolution orthophotos of Joko Marsh. We had access to 3-band imagery from 2018 and a full set of 4-band imagery with RGB and the infrared band from 2019. We also had access to the New York City land cover raster dataset, which we used to provide an initial mask to separate between land and water, as well as the New York City topobathymetric LiDAR dataset, which we use to generate a DEM layer to determine the elevation of different locations on the marsh. And finally, we had access to manually digitized laughing gull nest locations and ground truth nest locations for 2019 to aid of our visual examination to assess rule set performance. So our project was broken down into 2 phases. Phase 1 was the proof of concept phase, which was conducted on a subset of the 2018 imagery. Phase 2 was the 2019 rule set phase, which we conducted using the full set of 2019 imagery for our study area. And this separation was due to the aforementioned availability of the infrared band, which we only had access to for the 2019 imagery. Now, both phases use the same 3-stage workflow shown here, starting with the pre-processing stage. Now, pre-processing was conducted in ArcGIS Pro and involved preparing the input datasets for import and use in eCognition, which was the object-based image analysis software that I used to implement this project. It was also during this stage that I developed an image interpretation key, which I'll go into more detail in a minute. So once we had all our data sets prepared, the second stage was the rule set development stage. And this stage was conducted entirely in eCognition and was primarily concerned with examining my imagery and setting up the rule sets and thresholds that we use to extract laughing gull nests. And at the end of this stage, the output is a point feature class of nest objects, which we then evaluated. The last stage was the rule set evaluation stage. Now, this stage was again conducted in ArcGIS Pro, and the goal of this stage was to evaluate the success of our rule set through both a visual examination of the output using manually digitized and ground truth locations, as well as to create an error matrix using accuracy assessment points to quantitatively assess how well the rule set was performing. So backing up a little bit, you'll recall that I mentioned I created an image interpretation key. Now, an image interpretation key is a tool for defining the elements of image interpretation in the imagery that we are interested in to identify laughing gull nests. And for laughing gull nests, I identified 5 elements of image interpretation listed here on the left. So starting from the top, we have the site element. Because it's a saltwater marsh, the gulls choose nest locations that are above the normal tide line to avoid being washed out during tidal fluctuations. So filtering out low elevation areas gives us a good idea of where the gull nest will be found in the study area. I also use the tone element, which refers to the spectral characteristics of different objects in the imagery. And as you can see from this photograph of a laughing gull nest, nests in the marsh are primarily made up of dead vegetation. So by limiting our search to only light-turned objects, we can help further narrow down what is and what is not a laughing gull nest. Our third element that we use is size. Laughing gull nests are typically only 1 to 2 feet in diameter. So I use this as a threshold to help filter out large areas of dead vegetation that are clearly not nests. I also use the shape element of image interpretation, and compared to other objects in the marsh, zooming again on this picture, laughing gull nests are often rounded as the bird builds out the nest from that central egg cup throughout the breeding season. And although this is not as rounded as man-made features, it's still something we can look for while searching for nests in the aerial imagery to help further narrow down what is a nest and what is not a nest. And the final element I use is association. Since we are using high resolution aerial imagery, you can actually see the birds sitting on the nest. So our rule set takes advantage of this fact by extracting only nest objects which have laughing gulls sitting on them. So to give you an overview of what that looks like in action, the rule set's on the left and my imagery on the right. It starts out by segmenting the entire picture down into, or the entire set of imagery down into image objects. And then it applies the site element, separating them by the initial mask and then looking for areas that are above the elevation threshold. Then it measures objects by their tone to determine what's an area of dead vegetation as what is not, shown here in pink. Measures them by their size and shape. And then it gives us a class of potential nest objects. Now, once we complete that initial pass looking for nests, the rule set does a second pass examining objects at the sublevel to incorporate the association element of image interpretation and look for gulls sitting on the nest. So this rule set first takes the potential nest objects from the previous pass and segments them at a much finer level. It then looks for objects that match the tonal characteristics of a laughing gull, which are very bright in the imagery due to the white plumage. And it's shown here in orange. There's a couple gulls sitting on those nests. or potential goals. Once bright objects are identified, it then checks them against the size we expect of a laughing goal. Laughing goals are between 39 to 46 centimeters. So we search for white objects that fall within that threshold shown here in purple. So these are actually our goals sitting on the nest. And finally, it incorporates the association element by checking for the existence of those laughing goal objects within the boundary of a nest object. There are typically 1 to 2 laughing goals sitting on or attending each nest, so any potential nest with that many laughing goal objects, it classifies as a nest. So again, this is what it looks like in action, rule set on the left and imagery on the right, zoomed in even further so you can see what's going on. It takes those previous extracted potential nest objects, breaks them down even further, checks them for their tone, then checks them for their size, and then it checks for the existence of those goal objects on the potential nest objects and extracts them, colored here in blue. Now you'll notice it did miss one nest in the bottom there, which you can see does have goals sitting on it. So our rule set accounts for this. It checks to see if there are any potential missed nests just outside of the threshold we were looking for laughing goals, identifies that as a missed nest, and then checks to see if it is within 120 pixels of a successfully extracted nest object. And because laughing goals nest in clusters, we can then use this to add it to the feature class. And now we have our final feature class of nests. So now that we've talked about how it works, how well did the rule set perform? So beginning with our visual analysis of the results, after many iterations, our best performing rule set extracted approximately 4,000 nests from 2019 imagery. And within those results, we found that there were many well-defined nest objects. But we also noticed that there were errors of omission and a significant number of errors of commission. Often, starting with the errors of omission on the left here, these were often nests that were excluded due to an odd segmentation, which caused them to be missed when we measured things by their shape and size. There were also, like I said, a significant number of errors of commission. And on the right, you can see an example of a lot of these. These were often false nests that to the software appear similar to an actual nest. This is usually flotsam and other debris situated on or adjacent to objects that match all our other nest characteristics. So with those visual results in mind, we examined our rule set quantitatively using accuracy assessment points to generate an error matrix for each run and drill down further into what was going on. Of particular interest on these tables is the producer's accuracy, which is a measure of false negatives, and the user's accuracy, which is a measure of false positives, both of which are shown here in red. So starting with phase 1, this is our initial rule set. You can see that it functioned fairly well on the 2018 subset, although half of the objects extracted were not actually nests. Now at this point, our rule set did not incorporate those sublevel objects. Sublevel objects turned out to be a really important tool for our ability to extract nests, as incorporating them improved our rule set to our user's accuracy to 82% when it was incorporated, which is a 32% increase and a really great result. So with those results in hand, we moved on from phase 1 to phase 2 and scaled everything up from the 2018 imagery to the full set of 2019 imagery. Now directly applying that rule set to the full project study area showed that more tuning was needed, as the user's accuracy dropped significantly to 32%, which is well below what we would consider to be acceptable. The 2019 imagery, though, does have access to the infrared band, and we found that using NDVI led to another significant improvement of our results, increasing our user's accuracy up to 50% for the full study area. And after several more iterations and runs, we found that our best rule set had a 65% user's accuracy and a 97% producer's accuracy, which was obtained by restructuring the sublevel examination to the successive method that I just detailed earlier, and searching for missed nest objects. 65% appears to be the ceiling for our methodology using the 2019 set of imagery, as any attempts to further differentiate nest features resulted in significant decreases to our user's accuracy. So what do those results mean for our study, and what does this mean for object-based image analysis in the wildlife field? So getting back to our initial question, does object-based image analysis provide the benefits we hope for the Laughing Goat project? And I'd say yes, it does. Looking at it from an efficiency perspective, this is a big improvement over previous methods. The old method typically took 1 to 2 weeks to complete, which ArcGIS Pro brought down to about 3 to 4 days, but it still required 1 to 2 people working on the project full time. Using object-based image analysis, I was able to extract a usable feature class of nests in 1 to 2 days while only working on the project part-time. And this can be further reduced. Several of our data sets are reusable, and the software can be staged to run overnight, both of which will significantly cut down on the time to complete. Turning to human errors, commission and omission errors complicated a fully autonomous workflow, which is what we were hoping for initially. However, while a 65% user's accuracy is not as high as we would have liked, we also achieved a 97% producer's accuracy, which means that the majority of nests in the imagery are in there along with the false positives. And we feel that this is still a successful result, as it lends itself very well to a semi-autonomous workflow. The computer is good at doing the initial search, and while the computer has trouble with hard cases, for a person, it's much easier to tell what is and what is not a nest. This method would completely eliminate human error in the initial search, as the computer now gives us a well-grounded foundation to build off of. The user simply needs to verify final results and catch any missed nest objects, which is a much easier task than searching through the entire set of imagery with no guide. And now the final point is, how does this compare to other work, and what does this mean for object-based image analysis in the wildlife field? And looking at previous work, we found that our results are very similar to the conclusions drawn by earlier studies. A high number of errors of commission seems to be a common theme when looking for wildlife in the aerial imagery, due to how difficult it can be to differentiate natural features from each other. And a semi-autonomous methodology seems to be the best solution, which is something that the Sea Eagle project in particular also hit on. And I'd also like to point out that our study provides a foundation for future projects involving laughing gulls and other colonial nesting waterbirds to build off of, which adds to the growing body of literature documenting this technique. And there's clearly a need for these techniques in the wildlife field. Aerial surveying is only growing in popularity as drones make obtaining this imagery much more accessible. Furthermore, the efficiency and human error issues we dealt with persist. One recent project assessing black-vented shearwater nesting colonies found that it took about 20 days to find all the nests in their imagery. And so it's not hard to imagine how much of a benefit a technique like ours could provide to the wildlife field due to its extensibility to other nesting waterbirds, which is hopefully something that this project has helped facilitate. So that wraps it up for my presentation. I'd like to thank Doug for all of his help on this project. I know he's been very patient with me. And I'm open to any questions at this time.
Thanks, Ben. Audience, do we have questions?
Let me stop the share here real quick because I remember how difficult it was to find questions in the chat last time. Jennifer, are you going to try to publish these results? Yeah, actually. We're going to try to publish it in the journal of, one of the publications from the Wildlife Society. The society, what is it? Wildlife Society Bulletin, I believe is what it's called. Yeah.
Yep, the bulletin.
Is there a bird size limitation that determines how successful this process is? I actually had a threshold for largest as the largest we would expect from a gull and the smallest. I didn't really, the biggest limitation regarding the birds on the nest was we found that some objects had too many birds on them. So there's like a rule in there I didn't really get into trying to squish this into 15 minutes that helps make it more successful. Image resolution again, and any false positives based on the classification methods. Image resolution was 0.5 meters. I want to say. Any false positives based on the classification method. Yeah, there was a number of the false positives. And I would love to have higher resolution imagery if I could. If you look at it, it's pretty good. You can see the nest and the birds, and you can tell kind of where they're flying and when they're not flying, when they're just kind of sitting there based on the size, which helped filter out some of those false positives when you'd have a bird just like, it's pretty impressive to see if you go out and look over the marsh, they'll just swirl above where they're nesting. But yeah, we were hopeful to use drone imagery for this to improve the resolution, which would hopefully improve the classification and filter out some of those false positives. And that's something that, in the future, when we have better access to this and we can get the permissions to do that kind of stuff, I would hope to get that resolution up as high as possible. And I would imagine that would improve our classification further. Let me know if I've answered that as what you were asking there. Did you use Python to animate the flow process? I did not. really cool project. How plausible is it to fly a drone over that area to collect higher res imagery? Perhaps if that runway is taken out of ops for a brief period during a particular day, I imagine it's not possible to fly even a low altitude drone if there are any departures or arrivals on the runway. That's actually a good question. I kind of touched on it a little bit, but and as Doug has learned with this project, where it is and who's located in New York, who's located in the proximity of this marsh, there is a lot of stakeholders involved in this project, and a lot of people you got to ask permission for. New York City especially is very locked down on where they allow drones to fly right now. So yeah, we had it to the point where a drone was lined up, and we actually have somebody that USDA has hired as a drone pilot. So we're really looking to actually collect that imagery soon. It's not going to happen this year, obviously, due to the circumstances, but no, it is definitely feasible for them. I don't know if they'd shut down the whole runway for us, but and it depends on the traffic, but it's certainly feasible to get them to try to call Tower and set up a time to collect that imagery, because yeah, that would be really great if we could show how drones would improve it. Yeah, it's really just a matter of getting the ducks in a row.
Or the laughing gulls.
Or the laughing gulls, yes. Yeah, if you're able to fly a drone, would you attempt to use thermal imagery? Yeah. That would be a really neat component, and so we do a lot of wildlife management projects, not just at the airport, and we've been kicking around a lot of other ways to implement drones and perhaps use object-based image analysis to quickly identify species that we're interested in. The drone in particular, and that's also why we're excited about this technique, because I mean it works for the laughing gulls here, but now we have like a foundation of like, all right, we found out we can use it, or we have like a framework of how we can use this for laughing gulls. We're hopeful to extend that framework to the other species we manage. The biggest one we've been talking about is flying a drone to look for deer using thermal imaging, because we do a lot of that work at night. But yeah, no, thermal imaging would be something that we're definitely looking into using.
Okay. For students that are online now that are contemplating a capstone, I will say that Ben's capstone is a great example of how to leverage an initial class project. This work started really in an 883 project in Jarlath O'Neill Dunn's class on object-based image processing, and so Ben has really stuck with it over the past year, and his manuscript is very close to being submitted. So I encourage you to think about how to leverage your course projects into something that you can apply to your capstone. I do want to say thanks to all the advisors and the attendees today, students. I also want to congratulate our students. This is the culmination of their work in our program. I think they're excellent examples of the kind of high quality students that we have. And we're also, we're also sorry that they couldn't carry through and go to a conference, present, but this is the next best alternative, and we have really appreciated hearing the work both last evening and today. There'll be more of these symposiums in the fall as more of our students wrap up their projects and as we continue to deal with an abnormal situation where conferences are really challenging. I want to thank everyone for your attendance today, and look forward to, if you're a student and you're with us, look forward to your talk in the fall. And with that, I'll say goodbye and have a great rest of the day, and enjoy the rest of the balance of your summer.